Energy has made my life unmanageable. So I and my partner Margaret Bacher designed Jack's home, and Jack and I have studied with a lot of the same people. We go to Margaret and I go to the NESI conference in Boston every year to try to stay current with what's going on with building energy, and things change every year. It's really exciting. Like they had an award for net zero energy buildings that they started like 3 years ago, and they had like 2 applicants, and one of them didn't make the qualification, and this year they had like 20 applicants, and it's amazing how fast people are catching on to the fact that it's possible to do net zero energy buildings. Is that enough of an introduction? So I want you to introduce yourself. How many engineers are in the audience? How many builders are in the audience? Okay, how many homeowners? I guess we're all homeowners. How many people that drive hybrid vehicles? Okay, I'm getting to know who I'm speaking to. I want to know who the choir is that I'm speaking. Thanks, Jack. So Jack was talking about the process of designing buildings, and you know, as an architect, we used to design buildings where the architect would meet with the owner, we decide how to design the building, we designed it, and then we can engage the engineers to come in and try to stuff all the mechanical systems up in the unconditioned attic or down in the basement, and then run some crazy ductwork around to get it all connected. And now we think it makes so much more sense, because buildings are getting so much more intelligent, to bring everybody to the table at the beginning of the project and have them tell us where they want to put the mechanical system, and have the engineers involved, and have the builder say, you don't want to build it that way. That's a crazy way to, you know, it looks good on paper, but looking at the third dimension, it doesn't make any sense at all. So we have to really rethink that. And so there's a lot more intelligence that goes on before you even get into the design process to get to net zero. But as Jack was saying, a lot of this stuff, if you build a better building, it's going to be more sustainable, and it's going to actually pay for itself. So it's not so much how much more it's going to cost, but it's how it's going to perform. I think about the performance of buildings rather than just how they look. So which era are we going? Up, down?
Either way.
Okay, so some of the passive solar strategies that Jack's already talked about, orienting the long dimension of the building on the east-west axis, so you get a maximum solar exposure on the south side. You get a nice south-facing roof slope where you can put your PV on. Looking at this, the way the sun moves in the wintertime. Let's see if this works. In the wintertime, you've got a sun angle which is really shallow, and it's not going to hit, you know, that much. In the summertime, it's going to be moving around the house, so you get much more exposure on the east and west side of the house in the summertime than you do in the wintertime. And it's that low sun angle on the east and west that it can overheat houses. And you have to think about where you put the windows. So what we're really going to do is put most of your windows, at least half of your windows, in the south side of the house, and put maybe 50% on the east and west. And on the north side, you want to have some lighting for daylighting, for cross ventilation, but you're not going to get any heat gain from the windows on the north side of the house. You're going to get mostly heat loss in the wintertime. And then, if this is a building section, you can barely see these, but this is the line of the sun that would come in December 21st, your winter solstice. And that's going to give you, you want to have the overhang designed so you get the most of that light coming in and heating up. If you have a radiant slab, you're going to be able to capture that inside. But in the summertime, when you're worried about overheating, you want to make sure that this is June 21st, then you want to have that all of that heat energy outside the building. So you want to size your overhang and position of your windows so that you're going to capture the heat when it's beneficial to your performance of the building, and then protect you from it. So the east and west is really difficult because you got a low sun angle on the west that's going to be coming in, and it's maybe going to overheat that side of the house, so we have to think about that. Putting deciduous trees on the south side of the house that have leaves in the summertime is going to help you shade the house. Having evergreen trees on the north and the west side are going to shield the house from winter winds, so that all that makes sense. These are all sort of passive concepts that, you know, started a long time ago. People have been thinking about this before we even had photovoltaic panels. Infiltration is one of the biggest heat losses in conventional buildings that don't think about air sealing and everything. So you have a wind coming through is going to create negative pressure on the leeward side of the building. If you have a normal stack effect inside a house, you're going to get infiltration with air getting sucked in at the sill plate, and heat is going to be escaping out at the edge of the top plate. If you get a really good air-sealed envelope, then the stack effect becomes neutralized, and you don't get that stratification of air where the second floor is warmer than the first floor because you get the cold air coming in and drafting. So if you seal up and get a better air seal, then you're going to do it. If you have a combustion appliance inside the house, basically what you're doing is you're putting the whole house under negative pressure. And it's just going to be sucking in through every orifice to make up air with the combustion air that's going in. So we only think about sealed combustion appliances in net zero energy houses. And most of the houses, if you have a wood stove in it, maybe Jack can attest to that. If you have a wood stove, sometimes you have a problem with overheating because you just generate too much heat if you have a really super insulated house.
Yeah, it's real easy. We've got a little wood stove, and in our house, put 2 logs in it, and the house gets 4 degrees hotter in less than an hour. It heats really fast.
And it holds that heat because it has mass on the inside of the house with a radiant floor slab. It's going to capture that heat. I think during construction of your house, they were monitoring the temperature in their house, and during construction, I think you were heating the house with your hot water heater in the basement, which was running like just warm water through the radiant slab, and they lost power, and the pump wasn't running, and the temperature dropped in the house, a couple of degrees in a day. In a conventional house, you lose power, in a couple of hours, it would be like 20 degrees colder inside the house. So air tightness is really important, and the quality of glazing is important. And this is a lot of numbers that probably aren't going to mean a lot to everybody. But basically, on the south side of the house, you want to have a solar heat gain coefficient, which is high, so it's going to bring a lot of heat in. And on the west side, you want a solar heat gain coefficient, which is lower, so it's going to let less of that heat coming in. And these, you can see that the performance of the building, this is kilowatt hours per year. If you have a solar heat gain coefficient, which is high, you're going to use. I'm getting confused already. Let's forget about the numbers. But I think the principle is that on Jack's house, we tuned each window in the building to be appropriate for that facade and that exposure, and worked it out so that it would be giving him the maximum beneficial heat gain for that year. So selecting windows is really important. It's a very expensive part of the building envelope, so you have to think about what you're doing. If we find that it's really hard to get a good double hung window that seals well. Casement windows and awning windows, because they compress the gaskets as they close, and they have little levers that keep them tighter. You're going to get a much better performance out of those. Let's see. Okay, you're talking about the percentage. So if you, as far as the total percentage of window, you want to have maybe 15% of the total floor area in glazing, and maybe half of that is on the south side. I see a lot of buildings, they're just like all glass, and I'm just saying to myself, how can they say that this is a high-performance building? It's a radiator. They're just radiating all that heat to the outside. They can't do it with that amount of glass. It's just because glass is sexy, it looks good in pictures, and it's really, and if you're talking about high-rise buildings, that skin is a lot cheaper than building bricks and mortar and that kind of stuff. But that's the kind of percentage you're looking for, is you want to look for about 15%. And then all this treating heat coefficient. So in the windows, conventional windows are usually like double hung windows. They're double glazed. Maybe they have argon fill. Maybe they have low E coatings on that. But even with that, you can barely get to an R5. And does everybody know what an R value is for insulation? It's basically a measure of how well it resists the conducting. High numbers are good, low numbers are bad. So with the double glazed window, maybe you're going to get an R5 out of the center of the glass. The frame is going to perform differently. Maybe the frame is going to be an R2 or an R3 in a conventional wood window. So for a high performance building, we want a window that's going to be better than R5. Otherwise, it's going to be a weak link. You've got a really well-insulated wall, you've got all this air seal, but then you've got a window that's leaking heat to the outside. So you want to have the window performing at the same level that your walls are. So with triple glazing, you can step up to get an R6 or an R9 window relatively easily. They have performance windows now that are sort of experimental, that are like thermos bottles. They evacuate, instead of putting argon gas or krypton or something in between the glass, they evacuate it and they put little pillars in there to keep the glass panes from cracking as they come together. And they can get like an R20 out of that, which is basically what people are, better than what people are building walls out of. So think about this sexy building that's all glass. And maybe someday it will be a high performance building, but right now I don't think it's so good. So we have a wood window that's got an R2 and R3, and the frame is R2 or R3. But if the glass is R9, it's only going to perform as an R4, total window assembly. So we want to have the frame be as efficient as the glass itself. So picking the frame material is important. So this one is a European window. It's a vinyl window, which I'm not too wild about, but they've really broken it up into all these little chambers, which acts as an insulator so that cold isn't moving right through the frame. This one has wood, it's laminated. This section right here is polystyrene, and it's got cabins, so it's got a wooden clad on the outside, but it's a wood window on the inside. And it also has sun shading veins in between the glass layers. It's triple glazed. It's got 3 layers of glass here, and in this layer here, you've got a shading device built right into it. So it's pretty sexy, but they're pretty expensive. So maybe on a conventional window product, you're going to be spending maybe $500 a window, maybe less if it's vinyl. If you go to triple glazing and you go to tilt and turn windows, maybe you're going to be spending $1,000 or $1,500 per window. And so that adds up to be a big part of your construction budget. But if you can have a much more higher performing building envelope, maybe you don't need to have a furnace that's going to generate 60 or 70,000 BTUs per hour. Maybe a smaller cassette mini split system that Jack's going to talk about, which only generates 15 or 20,000 BTUs per hour, and it costs $3,000 rather than $20,000 or $25,000. So there's a trade-off there where you can balance the performance of the building by selecting and investing in, as Jack was saying, investing in the envelope, and then that's going to pay back with reduced energy costs as you get further along. So now we're going to talk about some of the details of construction, but also some of the principles. When we're thinking about designing the envelope, we think about the air barrier, we think about the thermal barrier, and the drainage plane. And these are sort of consistent elements of the wall assembly and the roof assembly. So the air barrier is what keeps the wind from blowing through the house. It's like thing you want to seal up and make continuous. Thermal barrier is like a blanket that keeps the heat in and the cold out, reverse in the summertime. And the drainage plane is how you manage water so that rainwater is not going to get into the wall and rot things out or degrade the insulation by making it soggy. So all these things are important things to tune when you're designing a window and a wall assembly. We also have to think when we get a really tight envelope, we have to think about indoor air quality. So we're probably talking about mechanical ventilation for makeup air and then heat recovery ventilation. We're also thinking about trapping moisture in the wall and making sure that if it does get wet, it can dry either to the inside or to the outside. Because I was talking to Jack before, old houses, you had a stud wall, and maybe you had lath and plaster on the inside, and maybe you had clapboards on the outside. No sheathing, no insulation, the wind blew through, you had plenty of fresh air. And then you try to insulate that same wall, and you've got problems because you start trapping moisture inside the wall. So here's a high-performance wall assembly, and this right here is what we're calling the air barrier. It's a red line. So this is a stud wall on the inside, and basically you have the sheathing wrapping around the outside of the building. And what you do is you've seen probably zip walls, it's the green and the orange sheathing, and you tape the joints between each of the panels on the outside of the building. And the tape is really high performance, it really sticks well. And basically that becomes your packaging. That's the shrink wrap that holds the whole thing together. And that's continuous from the ridge all the way down to the foundation. And then you have a thermal layer, which is your thermal barrier, which is like rigid insulation on the outside of that. And then you have your rain screen, which is your roofing and your sheeting, your siding, the cladding on the outside. And many times you see when you have rigid insulation, they'll have vertical furring strips, which is your drainage plane, where if water gets through the clapboards, it's going to hit that and be able to drain down and get outside the wall. And the beauty of this system having the air barrier right here and having the studs on the inside is that you have the opportunity to run all of your wiring and your plumbing in the exterior wall on the inside of the air barrier without penetrating it. So making the air sealing of the building a lot easier. If you have you're trying to do the air, there's other systems where you have airtight drywall, where you try to make the drywall on the inside your air barrier, but then if you have an electrical receptacle on the outside wall or plumbing in the wall, every time you have a penetration, you have to be very careful about sealing. Where here, you can throw insulation in here, and you can throw more attic insulation in here, but any penetration inside here is easy to do, and it's not going to threaten the integrity of your thermal blanket, because here's your thermal barriers outside of the air barrier.
That's a question.
Yes, sir.
Is the air barrier a vapor barrier?
Yes, in this case, it's both the air barrier and a vapor barrier. I'll get it eventually. So we got this wall assembly, and we're trying to insulate it. And you can do all kinds of great things with spray foam and polyiso insulation, which have a really high R value. But if you have studs that are in the wall, or you have a foundation that's sitting there with concrete here and brick on the outside, you have places what we call, a thermal bridge, where the warm air can just easily get to the outside. And so for having that, contrary to the previous slide where you have a continuous thermal barrier on the outside, here we've got an opening where heat can go up on the outside. And so if you look at this chart over here, you can't read them at all, but in these are two wood stud partitions over here. This is R21, R19, R15, and R11. Different thicknesses of insulation, but this is what you would have in a conventional 2x6 stud wall. You'd have R21 insulation in there. But the actual performance of that wall, because of the thermal bridging through there, you really only get about an R13 or R14 out of that wall. So you got much lower. If those are metal studs there, your R21 becomes R7. So basically those metal studs are like fins in a radiator. They're just radiating that heat right to the outside. So that's why we talk about the performance of the wall. We're thinking about all the elements in there. And some of those are working. You need the structure, but what you really want to have is continuous insulation on the outside of the structure to keep that from leaking. And then inside the stud wall, if this was a stud wall here, you also get the possibility of infiltration, which you want to stop with tape and sealants. We have convection loops inside the stud wall. If you put a fiberglass bat in a stud wall, there's all kinds of gaps around it. It doesn't fit tightly. So air can move in the wall and just create a convective loop, taking warm air from the inside and taking it to the outside skin and just transmitting the heat right through there. And radiant losses are when the window and the surface temperature of the inside of the wall, the exterior wall, is so cold that you can feel it just sort of wicking heat off of your face. You can feel the cold, just like standing in front of a wood stove, you can feel the warmth of that. But with the walls, the comfort of the occupants is reduced if all the surfaces of the exterior wall are cold. So many times we're asked, what's the best heating system to put in a building? And the answer that we try to come up with is the fact that the best heating system for a building is an R20 foundation wall, an R40 wall, and an R60 roof, and air sealed to the point where you get less than 1 air change per hour at 50 pascals. And that's a lot of gobbledygook, but it's just a really well-sealed building and a well-insulated building is going to perform so much better that sometimes you don't even need to have a heating system. I mean, these passive houses that that Jack was talking about in Germany, which is now a building standard for new construction in Germany. They can almost heat the building with light bulbs and the occupants. I mean, it's just amazing. They don't even need, I mean, they have a little bit of resistance heat in their heat recovery ventilation system, and that's probably all that they need. They get enough from sunlight, and the occupants and all the plug loads inside the building are generating enough heat. You don't even need a furnace. I mean, it's just amazing. So that's something to keep in mind when you're talking about having a really high-performance building. Some of the advanced framing techniques that some of the builders are using try to have less wood in the exterior wall. So not only have the exterior insulation, but have less wood. And so what they do is have single plates instead of double plates at the top. They have the rafters and the studs and the joists all lining up in the wall so that they can use less wood. It's a little bit chancy. I don't like it. I like a lot of wood. I'm a carpenter by training. I just like to see something that's really stable. But they can do it with cross bracing with steel bands and that kind of stuff, leaded bracing. But they can reduce the amount of wood in the exterior wall sometimes by 30%. So that means you can have 30% more insulation in the exterior wall, which makes a lot of sense. You can do the same thing with continuous insulation. You can do the same thing with other assemblies like insulated concrete forms, where you have 2 layers of polystyrene with a reinforced concrete core, like Lego blocks. You stack them up and you fill them with concrete. Or SIPs, structural insulated panels, where they have drywall skin and a plywood skin on the outside, and it's just polyurethane foam in between there. And they can have these big sheets that are really easy to air seal because it's just one panel that's maybe half of the roof. And just continuous exterior insulation is a great thing. So here we'll go through some of the foundation details, interior insulation, exterior insulation, and slab on grade. I'm sorry there aren't more builders in the audience, but it's just for the fun is all these details. But this is showing interior insulation. This is your foundation wall here. They have rigid insulation on the inside of the foundation. It's wrapped down underneath the floor slab, and it has basically a conventional stud wall inside that, and then your drywall on the inside of that. So basically, you have a continuous insulation here coming down, wrapping around there, and then you've got spray foam at the rim joist here to seal the space in between the floor joists and the exterior wall, and the sill, which is one of those places where a lot of cold air gets sucked in when you have a thermal chimney effect going on.
Until we lived in this house, I never had a house that had any insulation other in the sill plate. It was just the wood. And it's like big gap in the envelope, sucking the air and heat right out.
So here's an example with exterior insulation on the foundation wall. Many times when they first started talking about passive solar buildings, they wanted to capture as much of the mass of the building inside the thermal envelope to act as a heat wheel, so that if it got really hot during the day, it would stay cool in the house because the masonry was holding the constant temperature. If it got really cold at night, the mass would just sort of carry through. And in the case of Jack's house, when they lost the heating system altogether, the building still carried pretty well because it was well insulated, but it had enough mass, heat stored in the mass of the building that carried through. But if you put the insulation on the outside of the wall, you have some things you have to think about. Carpenter ants love polystyrene. They just love digging into it. Mice will live inside. We had a building that had the animal hospital that we did. It had insulated concrete forms, and they had mice in the basement that were burrowing into the insulation on the inside of the wall. So you have to think about that. You have to protect the insulation. Ultraviolet radiation will degrade polystyrene and polyurethane foam insulation on the outside, so you've got to put some kind of protection board to keep the beasties out of it and to protect it. And you also have to think about moisture on the outside of the building. A lot of insulation gets degraded if it gets saturated with water, so you have to think about protecting it from flashing it so the water is going to stay outside of that building envelope. And then there's slab on grade construction, and again, there's no foundation, there's just a stem wall for a frost wall, but there's no basement underneath there. So you've got insulation here underneath the slab and then wrapping up, and then you're going to have a sealant here which ties into the sill plate and then goes to the outside of the building. So then your air barrier just comes down, your thermal barrier wrap around, like that. So you're trying to eliminate thermal bridging through the foundation wall where we had that slide before. Crawl spaces are really tricky. This case, the thermal barrier is above the crawl space. Some crawl spaces insulate the exterior wall. Here we have it. On the floor joist, you still have to have some kind of moisture barrier here to keep moisture from the ground from coming up and condensing in here. A lot of code officials want to see a vent on the crawl space. By code it's required, but our experience in our house is that if you have ventilation in the basement and you have cold walls that are up against the earth, then they're going to act as a dehumidifier. So warm, moist air may move through in the summertime and just condense on the inside of the walls. So sometimes it's better to have it all sealed up and just run a dehumidifier in there to keep it, dry, because you don't want to have mold and all that good stuff growing in your basement. So the best solution then is to have one of those vents that has a little damper and you can just sort of slide it and close it off in the summertime, then open it up in the spring and fall and winter, let it dry out if there's any moisture in there. So let's talk about the wall assemblies. So we have a stud wall with exterior insulation, which we've talked about. A double stud wall, which is what Jack has in his house. And we have a stud wall with Larson trusses, which are basically horizontal trusses you turn on their side and just sort of pack out the wall on the outside. So the first one looks pretty conventional. Here's your stud wall on the inside, your sheathing, and then it has sealant to seal up the sheathing, and then this is your exterior insulation on the outside, which could be 1.5 inches, it could be 2 inches, it could be 4 inches or 6 inches, depending on how much insulation you can afford and how tight you want to have your house. Its ease of construction is high because it's just using conventional materials. You have to work about details, about pushing the windows out so that they're at the outside of the insulation, so you have to work on the flashing details around that. But it does eliminate the thermal bridging at the studs when you have the insulation on the outside, and you can apply some of those advanced framing techniques if you like that. So here's a double stud wall, and basically what this is, it's like a 2x4 stud wall on the outside, which you can erect the house, build a shell, put the roof on, and then you can come back and put another stud wall on the inside of that, creating a cavity which is 18, 12 inches, whatever thickness you need for the insulation, and then you can blow it full of dense packed cellulose insulation or fiberglass insulation and get whatever R value you want. So if your target is to get an R40 wall, you need to have about 12 inches of cellulose to get to that point. So this is one way of doing it.
And this is what we have.
But the downside of having a wall that's 12 inches thick, obviously, is that you're building a lot of house, but you're losing a lot of it in the thickness of the wall. So if I have a house that's 2-story and you've got 1,000 square feet on each floor, you're losing, depending on the proportions of it, like 100 to 200 square feet of space just in the exterior wall. So it's maybe like you're losing almost half a room or a room in the house. So you have to make a decision whether you want a high-performance house or you want just a big house to impress your friends. It's a tough call. Jack impressed his friends with his house, and it's in the big because it's high performance. You have to choose what's important to you. So again, this uses a little bit more wood, and you lose some of that floor space. So here's another alternative, what I call the Larson truss. And this is a conventional stud wall here, and it's got these truss members that are attached to the outside of the wall, and then basically this dense packed cellulose is on the outside of your sheathing, and it's hanging out over the foundation wall down here. And so in some cases that gives you that wall, but you don't have to build a bigger foundation, you don't have to have a bigger floor at each floor, you can just have trusses hang out. And it's really great because you get this continuity across the second floor rim joist. You can just run right by that with all your insulation. And it uses a little bit more wood, but you can get really high R values with it. And a lot of passive houses use this construction technique. Roof construction, okay, prefabricated wood trusses with a raised heel, basically a high stacked area above the top plate of the wall. Then we have sloped roofs with like vented cathedral ceiling or an unvented cathedral ceiling.
Could you, you said that last truss was good for retrofits.
Yes.
Could you just
have an existing house and you want to have a 12-inch thick wall, you have a lot of paneling on the inside of the house that you really like, you have traditional details, it's really easy to put that insulation on the outside of the house. So one thing you could do would be to just put layers of rigid insulation. But if you want to get a higher R value, if you put the Larson trusses on the outside, you can pack out 12 inches of insulation outside and not disturb the inside of the house. Depending on how you detail, you can even leave the windows in their current location, and you won't have to change the windows and push them out. If you put all the insulation on the inside, you'd be losing living space. You might be, losing so much space in a room that it wasn't really big enough for the space that you had before. Does that answer your question?
Yeah,
There's some pictures coming up, you'll
Okay.
see it better.
We can talk later too. I'm not going anywhere. I think. So this one. So this is actually shown as a double stud wall. It doesn't have to be a double stud wall, but you have an opportunity here to just build a conventional wall. This is the heel that I was talking about here. You would have a higher space here, so you don't lose insulation. Sometimes conventional trusses get really thin as they're coming down above the wall, and it squeezes the amount of insulation you put in there. So basically, you can build this, and this detail, you've got OSB in here, 3/4 inch, which allows you to then connect this to the drywall and get your air barrier to come right through here and then down there. So that's your air barrier going down there. This is your thermal barrier. Up here, you have to have some ventilation above that. But here, with the trusses, you can put in 12 inches, 18 inches, 24 inches of insulation just blown in there. You don't have to build any more structure. You can really max out the amount of insulation you can have in the wall. So these get a little bit tricky when you have a cathedral ceiling because you don't have that attic space. You don't have that free space that you can just blow insulation into. And you have to be careful about how you ventilate this space. So if you have an E-vent here, you've got to put a baffle in there so that air can move across here and then out the ridge of the roof. So that your thermal area is in here, you've got some rigid insulation there, you've got some rigid insulation on the outside of the wall. But if to try to get the air barrier to work through the wall here, it's got drywall here coming through the stud, and it's got some spray foam in here. It gets a little bit trickier than that truss where you can just have a continuous air barrier going right through there. Here's an unvented cathedral ceiling, this is showing a Larson truss on the outside with a stud wall here. And here the air barrier, you just go up here and you put spray foam in here to connect it to the sheeting. And then this is just rigid insulation on the outside, on the top of the wall, on top of the roof, and then you can fill this with insulation in there. So in wall assemblies and roof assemblies, code says you really should have an R20 rigid insulation or spray foam in direct contact with your exterior sheathing to avoid any condensation on the inside of the sheathing. Because you can get that wall really cold in the wintertime. The inside surface of that could be almost at ambient temperature outside the building. So if you have any moisture inside the building that's coming through, it could condense on the underside of that plywood and OSB. So if you have some rigid insulation up here, it's going to keep that condensation from happening because the inside temperature is going to be high enough that it's not going to condense there. Okay, here's some pictures of construction details, and maybe it'll help you understand the Larson truss a little better. This is just a conventional cast-in-place concrete wall with a spray application of waterproofing on the outside, some rigid insulation on the outside. This is a gravel bed with a drainage tile in there, and you usually want to wrap that with geotextile fabric to keep that so that it'll keep draining water that it finds from the soil won't go in there and choke it up. Here are some details. This is a wall on a house we designed that had the insulated concrete forms in it. You can see it's just like blocks you stack up. They all interconnect. They have ribs in there that you can screw the interior finish and the exterior finish in. You pour it full of concrete and you're done. In this house, we use that for the foundation and the first and second floor walls. But again, you have to worry about protecting the outside of the foundation wall with a stucco application or something to keep the bugs out of it. Here's a radiant floor slab where they had a matrix on top of polystyrene where you can just lay your radiant tubing right in the joints in between the grid. I would have told the builder to put a lot more insulation underneath there. You only think he has 1.5 inches of polystyrene, which is nothing. He's spending some money heating up the ground in that place, but he does have a lot of insulation in the perimeter because the frost walls of the ICFs going all the way down, but I think they should have had more insulation there. So here's the ICFs on the inside, and you can see you really have to cut slots to get your wiring. If you want to have a receptacle on the outside wall, so you're losing a little bit of insulation there. But it's a great system because there's something about the continuity of the structure of the thermal envelope. It's all like right there and going right through the building, the foundation, first floor, second floor. Here's that new construction where we have exterior insulation. You can see that all the joints are taped in between all of the sheets of the Armax insulation on the outside, and it has the vertical furring strips that are your drainage planes, and you put your cladding on over that. Any moisture that gets through there is going to come down in that space. You have to be very careful where you have windows that are pushed out like that to make sure you have the flashing details over. I'm not seeing an awful lot of flashing around the windows, but I'm hoping it's in behind there in this particular case. This is a retrofit of a basement where they just put the rigid insulation on the inside of the foundation wall. They just studded it out conventionally with inside. It was studs on the inside of that, and then you can put more fiberglass insulation in the cavity. And the detail at the bottom, you have some type of a capillary break here. Either this is just a strip of rigid insulation, or you can use Trex or something else that won't wick moisture up from the concrete into the wall and then create mold in a basement situation. Here's a retrofit above grade wall and a historic home that had a lot of nice details on the outside. They put rigid insulation on the outside. They moved all the windows out. They put stripping in there, and then they put clapboard siding on the outside of that. So when they were all done, they had a house that really looked much like it was before they did the renovation. It took a lot of effort to do that, but it's not impossible to do that in a retrofit situation. Again, in this case, on a retrofit, they chose to put rigid insulation on the walls and rigid insulation on the roof, and they cut off all the roof overhangs so that they could get this continuity of the air barrier and thermal barrier right around the corner, the junction between the wall and the roof. And then you say, well, how do you put an eave or a gutter on the edge of that? And so what you do is you, on top of that additional insulation, they put another layer of sheathing, which cantilevers out over beyond the insulation, and then you can attach your brackets to get the gutters and the edges of the roof trim back on. And here's a picture of the Larson trusses on the outside, which give you a little bit better idea of what's going on here. So this is the wall plane there, and then these are all sticking out beyond that, and there'll be another piece that'll be going in here to take it up to the edge of the roof. But you get an idea, you can blow a lot of insulation in there and get it up. In this particular site, they had a zoning restriction on the footprint of the building. They could only build out so much. So what they did is they told them what the foundation was, and then they put all the insulation on the outside of it. So they were to build, another room basically in their house because they put all that insulation outboard with sheathing. And here's a detail at the bottom of that wall. They were going to blow cellulose insulation in that cavity, but they wanted to make sure they vented it, so they have some slots in the bottom here so they have some drainage so any accumulated moisture in there can get out. So that's an important consideration of, if the moisture gets in there, to be able to have a path for it to get out. I think we're ready for it. Any questions? Yes, sir.
Stress panels? Okay. And then another question, second part, rock salt insulation, that mineral-based insulation, do you ever use that?
I think did we use any of that in your house?
We used a little bit of it in places where the insulation can get wet. We used that on the exterior of the foundation as a insulation.
So it's not as good as fiberglass, is that what you're?
Well, for exterior foundation walls is the only place that I would propose using it, because it can maintain some of its insulating value even when it takes on moisture. But it's not degraded by moisture. You don't have to worry about rodents or ants getting in there because they don't burrow into it the same way they do styrofoam, because it's usually a little bit denser than that.
So why don't you use it in more parts of the house?
It's a little bit more expensive. It's a little bit harder to cut. I think that for exterior continuous insulation, the boards that you can tape the joints are preferable. But for below grade applications, There's a great book I can refer you to from Green Building that has this whole thing about selecting different insulations for different applications. I can give you a link to that, and that's really helpful to show you all the different selections you have and where they're appropriate. Have you used it before?
Oh, yeah, use it all the time. And what about stress panels?
So, SIPS panels, you're saying?
Stress panels, you know where they have the,
Extruded.
yeah, they have the,
Structural panels.
the
Structural insulated panels.
OSB on the outside,
Mhm.
and they have a foot of polish, and then they have OSB on
Drywall.
the inside.
Right.
So it's a-
So
Comes
we-
with big slabs.
We've seen those on our buildings, and they are wonderful. I think they work really well if you have a braced frame building where you want to expose the structure on the inside, like a barn frame. And you can put the stress skins on the outside. You can span, large distances with them, so you can, span 8, 10 feet, sometimes 12 feet between joists or purlins for the roof. So they're great for that. The one thing you have to be very careful about with SIPs is the connections where the joints come together. They tell you that many of them have splines you can put in there to bring them together to join the panel, but then you're supposed to put spray foam in there or something to seal it up. And if you don't do a really good job there, and the water gets in there, it can rot out the whole panel, and then what do? You're really stuck. You don't have something to fall back on. You really got to disassemble the whole building to replace that section. So they're great if they're installed, really well. Did you have the same question?
That's the same question.
Anything else? Okay, we've got coffee, cookies. What do we have?
We'll take 5 to 8 minutes and be back at 8:15, okay?